Hello, everyone. Welcome to the second of our series of 6 webinars about science and policy. I'm Michael Mitchell, Project Manager for the Coalition for Rainforest Nations. Last week, we heard about the Intergovernmental Panel on Climate Change, the IPCC, its structure, what it produces, and how. Today, we will focus on what factors determine the climate of the Earth, what is the role of greenhouse gases, their trends, and anthropogenic drivers. We will be covering a lot of the latest scientific data produced by the IPCC. So if you have any questions, please use the raise hand option at the bottom of your screen or add questions to the chat, and we will address those at the appropriate times. Be advised, this will be recorded and used for future training purposes. I'm here today with Thelma Krug, Vice Chair of the IPCC and Senior Technical Expert for the Coalition for Rainforest Nations. Happy to have you back this week, Thelma.
Yeah, thanks, Michael, and really happy to be here. And let me say hello to all the participants.
So let's begin. So some of you may have heard of the term climate system and how human activities are continuing to alter it. For those of you who have not heard the term, Thelma, what is the climate system?
Well, the climate system is a complex system and has many components. The atmosphere, the land surface, snow and ice, ocean and water bodies, and also the living things, all interacting among themselves. So a change in the land surface, for instance, can affect the atmosphere, the ocean, and so on. And the atmospheric component of the climate system is the one that most obviously characterizes climate.
Well, obviously, we all know what climate is or have a good idea, but how would you describe it scientifically?
Well, climate is normally described by the characteristics of some climate variables. So, for instance, the average of global temperature, the variance of global precipitation, but this is over a period of time that ranges from months to millions of years, but it's traditionally 20 to 30 years. Well, and this is why some people say the climate is the average weather.
So seasonal variances from one year to the next are not necessarily changes in climate, right?
Well, this is a common misconception. In every 1 year, it's normal to have very cold days and very hot days as well. So if you take the average of the daily surface temperatures throughout the year, and then again in the next years, and you do so for, say, 20, 30 years, and if you do not see an increasing or decreasing trend in the mean or a change in the variance, you can say that you have a stationary climate. A non-stationary climate would mean that what used to be normal is not normal anymore. So you may be having systematically more hot days or more cold days that alter the average of the mean temperature in that period that I mentioned, 20, 30 years. It could be longer or shorter period of time. So look at the figure in this slide where you can visualize the difference. Although you may have any differences in temperature, precipitation, or other climate variables, say wind, for instance, the mean does not change during the time frame we are describing or we are observing. But the slide on the right-hand side, then you can see a clear increasing trend in the mean, and in particular after the 1960s. Yeah.
Are the changes we're experiencing in the climate system now all due to human influence?
Well, not only. The climate system has its own internal dynamics, but is also influenced by external factors that affect the climate. We normally refer to these as forcings.
Because you mentioned external factors. What are those?
Well, external factors can be natural phenomena, for instance, volcanic eruptions, solar variations, but they can also be human activities that change the composition of the atmosphere. For instance, deforestation, fossil fuel use for energy transport, cattle ranching. Well, I'm just naming a few of them.
You said that volcanic eruptions are an example of a natural external factor that can change the climate. Do these eruptions warm or cool the Earth?
Aha, this is an interesting question. And so why don't we give a chance for the participants to write what they think?
Okay, it's poll time for everyone there. We'll put a question up on the board for you all to submit. They're all anonymous. Let's see what everyone thinks. Do volcanic eruptions warm or cool the Earth? So we've got a few responses here. They're still coming in. It looks like the majority are saying that they cool the Earth. Thelma?
And then, and then we can see also some answer that it warms or that have no impact. Well, warming up is coming up. Yeah, but in fact, Michael, it cools the global temperature. But then you can ask me, why does this happen? But the explanation is reasonably simple. Major volcanic eruptions eject material very high into the atmosphere and cause dramatic changes in the amount of fine particles. We also call them aerosols that reflect sunlight. So when the solar radiation meets an aerosol particle, it bounces back to space, avoiding the radiation reaching the Earth's surface. So the impact can be a cooling for, well, some months or even years.
Wow. So how can the climate system be changed?
Well, solar radiation is the dominant source of energy into the system. The climate system is powered by the sun. So when one alters the radiation balance of the Earth, and so what is this? Is when you are changing the energy, the energy that is coming in, the energy that's lost to space, and how much remain on Earth and the atmosphere. All this can affect the climate system. So there are fundamentally three ways the radiation balance of the Earth can be changed. One is when the changes in the sun, changes in the orbit of the Earth, for instance, change the incoming solar radiation, the energy that reaches the atmosphere and the surface, right? Another one is when the fraction of solar radiation reflected by a surface is changed, and we call this albedo. Well, Michael, you may have heard about this before.
Okay, well, just in case some people don't know, like me, for instance, please tell us.
Well, don't worry. I will provide an example. So, for instance, snow-covered surfaces with those white, beautiful flakes, they reflect a high percentage of the solar radiation. We say these surfaces have a high albedo. On the other hand, vegetation-covered surfaces, which are darker, have a low albedo. So the fraction of the solar radiation they reflect is lower than those from the ice-covered surfaces. But you know what, Michael? I guess this is why people say we should wear white clothing in hot days. It is like snow. But I guess there is more into this, so let's go to the third way. The radiation balance of the Earth can be changed. And that is by altering the infrared radiation from Earth back to space. And how would this happen? Well, by changing the concentration of the so-called greenhouse gases, which trap part of the infrared heat energy. They are heat-trapping gases.
So the climate responds directly to these changes you mentioned.
Yes, directly, but also indirectly through a range of feedback mechanisms. I will explain that, okay? I'm going to give an example. So as the climate on Earth gets warmer, What happens to the snow and ice? They begin to melt, right? And as they do, the darker surfaces and water surfaces beneath the snow and ice, they appear and absorb more of the sun's heat. And this causes more warming, which causes more melting, and so on. So it's a self-reinforcing cycle. And one of the important uncertainties about the future warming is exactly the melting of the permafrost areas, the areas with ice and snow.
And how much of the sunlight is actually reflected back to space?
About 30% of the sunlight that reaches the top of the atmosphere, we are talking about 100 kilometers above the Earth's surface, is reflected back to space. Two-thirds of these because of the presence of clouds and aerosols in the atmosphere. And the remaining one-third due to the light-colored areas of their surface. So we are now talking again about the snow, the ice, and also the deserts. Do you remember when we mentioned that these surfaces have high albedo and reflect back a good fraction of the solar radiation?
Yes, I remember. But what happens to the energy that's not reflected back to space?
That energy is absorbed by the Earth's surface and also the atmosphere. So this amounts to approximately 240 watts per square meter. It's like you placing a bulb, a lamp with 240 watts in every square meter, and this warms the ground. So to balance out this incoming energy, the Earth must radiate, on average, the same amount of energy back to space. And does this by emitting this long wave radiation in the form of infrared light. So everything on Earth emits long wave radiation continuously.
So approximately 240 watts per square meter is absorbed by the Earth's surface and the atmosphere. So in principle, the same amount should be emitted back to space. Is that correct?
Yeah, but to emit this amount of energy back, the surface would have to have a temperature of minus 19 degrees Celsius, which is much colder than the main surface temperature of approximately 14 degrees Celsius that we have on the Earth's surface.
And what exactly are these gases?
Well, let me explain to you why is it that the surface is then not minus 19 degrees Celsius, but 14 degrees Celsius? And that is when the greenhouse gases we so much hear about enter into play. So these gases form a partial blanket to the long wave radiation coming from the surface that wants to go out, but is blocked. So this creates a natural greenhouse gas effect.
Oh, okay. So yeah, so then we get into what these gases actually are.
Yeah, there are several of them, including water vapor. So some people would say, well, I didn't know about this being a greenhouse gas. Yes, it's very abundant, but it's a naturally occurring greenhouse gas. But we also have carbon dioxide. These are the main greenhouse gases that you see in the atmosphere.
So nitrogen and oxygen are also very abundant in the atmosphere. Are they considered greenhouse gases as well?
Yeah, they are very abundant, but they do not have this effect. But human activities can release these greenhouse gases and intensify the blanketing effect that I have mentioned before. So for instance, since pre-industrial times, the concentration of carbon dioxide in the atmosphere has increased by about 47%. And due to human activities, mainly from the combustion of fossil fuels and land use change, and in this case, mainly deforestation. So we see that humans have dramatically altered the chemical composition of the global atmosphere. And this has had significant implications for the climate. And this slide is one of my favorites, Michael. Yeah, because it shows so clearly the evolution of the anthropogenic, human-related CO2 emissions since 1850, and this is in billions of tons per year. And one can see how much comes from fossil fuels, and that is in gray, and from forestry and other land use that you see in brown. This slide goes only up to 2012. It comes from a previous IPCC report from 2013. But I really love to see this one because it gives you a very good idea who is who in this climate change business.
Look at the spike in fossil fuels there. If that's not a reason to buy electric cars next, I don't know. I don't know what is. Did the latest IPCC report update the information on greenhouse gases in the atmosphere? And are they reducing or increasing? I'm reluctantly assuming they aren't reducing, right?
Michael, I would love to say they are reducing, which would imply that their concentration in the atmosphere is not increasing, but unfortunately not. So look at the figure in this slide that comes from the just released IPCC report you have mentioned. And this slide is now stretching the atmospheric CO2 concentration data up to 2020, so it's quite recent. So pay attention only to the curve that is steadily increasing, not the red one, okay? So all those different colors that you see in the box, it refers to places or sources where atmospheric data are collected and are archived. So for instance, Mauna Loa has the longest atmospheric data or record of direct measurements of CO2 in the atmosphere. But you also have data from South Pole that have been recorded since 1957. But in this long 60-year sequence of CO2 records, we can also see data from GOSAT, a greenhouse gases observing satellite that was launched by Japan in 2009. It was the first one to measure the concentration of CO2, and it's still operational. And this is why the green line you see in the figure, it starts later than the other records. But what's really impressive is the consistency between this data collected from independent sources, and unfortunately showing this increasing trend in the concentration. So look also that the figures refer to concentrations, right? So the units you're seeing is in ppm. And what does this mean? Parts per million. So for instance, 350 ppm means that you have 350 molecules of CO2 per 1 million molecules of dry air.
There are other greenhouse gases besides CO2, right?
Yeah, sure. CO2 is the most abundant. I used to say also that it's perverse. This is not really very scientific. But why do I say that? Because part of the emissions of the CO2 remains in the atmosphere for millions of years. So compare it to methane, which stays in the atmosphere for 13, 14 years. It's really a very long lifetime.
So now can we look at the other gases and how they originate and exactly where do we stand with those?
Yeah, sure, Michael. So let's see methane, CH4, and then what you see is also coming from different sources. So it shows the concentration of CH4 in the atmosphere, also up to 2020, and also coming from the assessment of the latest IPCC report. So this slide shows the concentration of CH4, and note that the units here of the concentration is different from that used for CO2. There you saw ppm, here you see ppb, which means part per billion. So 1600 ppb means 1600 molecules of methane is in the atmosphere for 1 billion molecules of dry air. So you see that there is much more carbon dioxide molecules in the atmosphere than methane. So you also see that the concentration of methane is more variable than those that we saw for the carbon dioxide. So the IPCC report indicates some of the reasons for these changes. For instance, The highest growth rate for the methane was in the period 1977 to 1986 and resulted from the so-called Green Revolution. It caused an increase in crop production and also a fast rate of industrialization that resulted in rapid increases in methane emissions coming from ruminant animals, rice cultivation, landfills, wetlands, oil and gas industry, and coal mining. Besides these, the decay of organic waste in solid waste landfills also emits methane. And those that are engaged in national greenhouse gas inventories use the IPCC guidelines and guidance to estimate and report emissions from each one of these sources.
So we're seeing the direct relation between human activities and the emissions of greenhouse gases. So how about last, nitrous oxide?
Well, nitrous oxide, N2O, has a lower concentration in the atmosphere than methane, and it's also stressed in ppb units. The largest anthropogenic source of N2O is agriculture, and its concentration, which has increased more than 45% since 1980s, is mainly due to the increased use of nitrogen fertilizer and manure management on cropland and pasture, but can also result from combustion, also from fossil fuels, and also solid waste.
Well, I have to say these increases are very concerning and directly related to the warming we've been experiencing for some time now, global warming.
Yes, and one of the results in the IPCC report just released is that the increases in greenhouse gas concentrations observed since pre-industrial times are unequivocally caused by human activities. So now we have a much more advanced understanding of the connections between the emissions we release, the rise in global surface temperature, and the changes to weather and climate we are seeing all around the world. IPCC confirms that the human-caused emissions of greenhouse gases are the main drivers of global warming. And these can be individually attributed to carbon dioxide, methane, and other greenhouse gases. And most of it indeed comes from CO2. And this is to meet energy supply and demand, transport, buildings, industry, you name it.
This data is fascinating and scary at the same time. But still, some people think that the warming could be attributed to natural causes, like those you mentioned, volcanic eruptions, solar variations, things like that.
Yes, you know something, Michael. The simulations of the changes in the global surface temperature by climate models that use only natural factors, like, for instance, volcanic eruptions, changes in the sun, cannot reproduce the actual observed changes, and in particular, since 1950. But the simulations are quite consistent with the observations if the human and natural factors are incorporated. So this slide shows the observations in black and the simulated changes using only natural factors. The line you see in blue is the range, and natural and human factors you see in brown, also within a range. As you can see, the blue line does not even get close to the observations shown in black, which can be, well reproduced by the simulated using human and natural factors. So I hope that explains.
It did, and I definitely in this 24 minutes have learned a lot and enjoyed it, and I hope everyone out there also enjoyed it as well. Now will be a great time. If you have any questions, please raise your hands. I know we covered quite a bit today, but we're happy to answer them. Just let us know. So perhaps you did a great job at you're describing everything. I have maybe just a couple questions someone might be into. So what elements exactly of the climate system have changed to date?
Basically, everything has changed. So what do you see now? You see a decreasing volume of the glaciers. You see the loss of the Arctic sea ice. You see the increase of the temperature over land and ocean. So you're changing the atmospheric concentration of greenhouse gases. You see the warming of the ocean with, you see with deoxygenation, as they say, and acidification of the oceans. So there are so many elements in the climate system that has been impacted already, Michael.
And with the ocean, like what causes the changes in the ocean exactly?
The ocean is an important element of the climate system, as well as everyone has its importance, right? But why do I say it is important? Because in fact, of the annual emissions that you have, particularly CO2, okay? Today, about 23% of these emissions of CO2 are taken up by the ocean. And this is the reason why the ocean is acidifying and causing all the impacts in the coral reefs. And also deoxygenation. It's because they are taking up some good portion, I would say, of that. But also a very good portion is also taken up by the terrestrial biosphere. And today I would say it's about 30%. So together, ocean and the terrestrial biosphere make up to approximately 56% of the taking up of CO2 from the atmosphere. If it weren't for that, you can imagine that what you would have in the atmosphere would be much worse than what we have been able to show today, Michael.
Well, we have quite a battle ahead of us, that's for sure. So I don't see any other questions have come in. Any last minutes? If not, I thank you all for doing your part to help fight the climate crisis. Of course, we're all in this together. Join us next week, same day, same time. We're going to discuss the Paris Agreement, the pros and cons of the new climate regime with our senior policy expert, Leo Masai. Details will be sent for those soon. And please share those details with your colleagues and friends. And I hope you all have a great weekend. Thank you. Thank you,
Thanks,
Thelma.
everyone. Really happy to be here. Hope it was helpful. Yeah, bye-bye.
It was. Bye-bye.